Okay, you can hear me well, right?
Yes, we can hear you perfectly. In
Sure.
which case,
Okay.
let's make a start. I'll introduce Rohit. Rohit, I'd rather you explain to the audience who you are, and we'll go from there. Um, and then hopefully you need to keep your time accurate. I think everybody's got 30 minutes. Okay, off you go.
All right. So let me get started. So good morning, good afternoon, everyone. So this is Rohit Sinha, and I'm working for Intel now. I have around 17 years of experience in the front end, ASIC design, and the methodology side, right? So I'm going to talk about enhancing quality and coverage of CDC closure in Intel's SoC design. We are a SoC group of design, and we are handling multiple client of products, right? So to begin with, I want to ensure that what exactly we are talking about. We are going to talk about CDC quality and the coverage. So we have kind of developed some mechanism that year on year we have multiple chips which are taped out with the CDC sign off, right? But every time we see multiple silicon sightings, right? So the whole attempt is to enhance the quality of the CDC sign off. And how do we ensure that the CDC is quality can be quantified, right? So the first one, right, what exactly we have developed as a methodology, right? So we call it design independent quality check. So the first one, right, I call it DIQC. So when we say design independent quality check, when we have the abstract model or the hierarchical model coming from multiple IP vendors, it could be internal, it could be external. So how do we ensure, right, when we source the abstract model in our SoC environment, right, we need to make sure that should not be any quality issues, right? So the first attempt is to identify upfront, even before getting the SoC integration done. We need to ensure that your the abstract model quality is good enough to be consumed. The second one is the waiver to constraints, right? So we have had thousands of waivers. Like in the last SoC design, we had around 61,000 of waivers. So we need to understand that whether the waivers are actually good practice to do, or we need to have an enhanced methodology where we can ensure that our waivers are not actually deployed in a mass manner. Rather, we are using the CDC constraint in order to capture the design intent, right? So once we have the CDC constraints instead of the waivers, we actually go for the CDC validation, wherein we actually develop the SVA protocol, SVA assertions, and that can be validated in the simulation environment. And that is one of the methodology, right? We develop end-to-end goal wherein most of our waivers are translated into constraints, and those constraints are actually validated into the simulation environment. The next one is the multi-mode CDC analysis. When we say multi-mode, right, in the past, in most of our project, right, we only have the functional mode of operation wherein we do the CDC sign off a single mode. However, our designs are actually in the multiple mode, wherein the DFT modes, the tap mode, the DFD, the visa, the bypass mode. So even in the functional modes, there are multiple modes of operation, and therein the multi-mode analysis is really a important or mandatory thing to do, so that we don't miss any coverage, right? We don't miss any metastability issues in any modes of operation, right? And the fifth one is the handling of waivers. When we say waivers, handling of parameters, when we say parameters, right, if you see, most of the design comes with the strap parameter, the width parameter, the modal, the control parameter. So there are multiple flavors of parameter. But if you see, when we source the parameters, it comes from multiple flavors, right? Some of the flavors of the parameters, they may not be used for the CDC analysis, right? So for those ones, we don't need to get and regenerate the abstract model for that parameter, for that function, right? So that the whole idea is, how do we reduce the turnaround time so that if there are redundant parameters change and SoC requirements are changing, you don't need to go and ask the IP vendor to provide you every time the new hierarchical model or the abstract model, right? And the sixth one is the power over analysis. We all understand that our CDC functional domain analysis does not get analyzed with the UPF instrumented power cells, right? If the power cells are not instrumented, our CDC assumptions does not hold good, right? Some of the already existing synchronized path may come as a glitchy path, right? Some of the already exist, and now there could be a new path because of the power control logic, right? So we need to ensure our CDC analysis in the front end itself is actually power aware, right? And also the metasim, right? We also do the validation domain, that random delay simulation, wherein we assume some of the cycles and we inject the fault, right? And we see the output of the deterministic model is actually with the glitches or unstable or not, right? So to continue with the design independent quality check, the first one I talked about, right? So uh, in this methodology, what we are talking about, since we have a huge handoff issues, right, from IP to subsystem, then subsystem to SoC, so there is a long handoff chain, right? Now IP has a different milestone, the subsystem has a different milestone, and SoC consumes, and they have to ensure that they are at the right model, right milestone, and right version, right? So every time we ensure that whenever we source any of the IP or subsystem abstract model, right, there should not be any issues. Any abstract model should not be left with any violation, right? So upfront we give the feedback. So earlier, every time we have to go through the integration process wherein the CDC run is completed, it flags some violation, and then if we give the feedback to the IP guys or the subsystem guy, and the loop is really long, right? And debugging at the customer end, that creates even a longer loop, right? The whole idea of the DIQC is, you actually read in. We have a automation wherein we read in all the abstract model violations, and we ensure that if there are any error remaining, we just get the feedback to the IP owners, and we ensure that all your abstract models are clean with no errors, no violations, right? If there are any existing violation, the feedback loop is much more shortened, right? Going next is the conversion of waivers to CDC constraint. The biggest pain point what we have had is the waivers what we use, it can't be reviewed or it can't be validated, right? And there are a huge number of waivers in our SoC design. So what methodology initiative what we have done is, we actually try to understand and bucketize what are the entire set of waivers which have been commonly used, right? And those commonly used waivers we actually translated into the equivalent constraint. So if you see, I'm not going to go each and every one, but if you have a stable and non-glitch prone signal, then you write a quasi-static signal. You have a pulse extender, then you define a clock relation. Similarly, you have a metaflop in crossing, right? So in that case, we use the enable multi-flop sync. So there are multiple, so there are always a one-to-one mapping. So we bucketized all the waivers into some categories, and we wrote equivalent constraints. The reason why we have done this practice, because this is a humongous effort, right? But what we have done is, we have created a practice wherein all your constraints are actually capturing the design intent. So whatever the architectural specification and the design intent was done to close the CDC analysis, those are captured into into the constraints, right? And that helps in reducing the review effort. You don't have to go and review each and every waivers, because it's a next to impossible task, right? Also, the waivers were the post processing of the analysis, right? Now there is a huge runtime gain because the constraints are applied much before your CDC analysis. That's the reason you don't have to go and post process the reports, right? And the biggest advantage, again I'm stressing the fact that the biggest advantage of translating all the waivers into constraints is, the constraints, there is a mode that all your constraints can be validated in the validation domain, and that is where the biggest value addition is, right? So going next, handling reset and reset sequences. So we have had multiple challenges in terms of reset, because whenever we have a RDC analysis, we have the RDC analysis throws millions of violation. Once we see the millions of violation, this is really overwhelming, right? So we need to understand, and we developed a step-to-step approach and methodology, step-to-step process, right? How do we handle these reset issues and the sequences issue, and then the RDC issues, right? So the first two issue, I mean, in the front, right, these are the construction issues. When we say construction, it is like reset distribution, wherein your primary reset, the derived reset, those are coming from the same domain. There's no domain conflicts. All these reset issues, right? These are construction issues, can be upfront caught. And once you resolve these ones, 70% of your reset problems will get solved, right? Because most of the, because IP to SoC handoff, right, there are a lot of propagation issues, so construction issues keep coming, right? The next one is the reset definition. When we say reset definition, in the previous projects, right, we never had any mechanism to define the architectural reset specification, which are coming from the power unit or the CPR block. These kind of reset definitions, right, these are very much well defined in the master clock spreadsheet, where we define all the reset and the derived reset. And this master clock spreadsheet is input to the CDC tool, right? And then we have a micro architectural specification document, wherein we defined all the reset sequences, right? Reset ordering, how the assertion and deassertion sequences are actually defined in the architecture, right? Once we have this information, it is a very easy task for the CDC owner to develop constraints out of these MCSS, which is master clock spreadsheet, and the MAS, which is micro architectural specification document. So the CDC owner upfront, right, it defines all the reset orders, right? And also, if there are some reset crossings which are very much known that there is no deassertion issues, there are no synchronization issues, right? So they therein we define the reset filter paths for all such issues, right? So defining these, right, it upfront clarifies a lot of issues. For example, now we are only left with thousands of violations. That's it. Earlier we started with millions, right? So now we just have to further define the reset sequences and assertion orders, and that helps in reducing the RDC paths. And only from that information, it is very easy to sign off our CDC for RDC analysis, right? Going next, so multi-mode CDC analysis. As I discussed, traditionally our CDC has always been done with one mode of operation. And in since CDC tool is a static tool, right? It actually assumes each sequential element, it only receives single clock domain. But in the reality, it is not true, right? We all know that there are multiple modes of operations, and we need to have in the static domain, we have to have a lot of set case analysis that will ensure that mode of operation is in single mode, right? But that is not sufficient. And that's the reason we have had multiple silicon sightings in Intel SoC design. And that's mainly because the CDC owner has only signed off in single domain, a single operation, single mode, right? Rather, they should have done with multiple modes, right? And from my perspective, CDC should also be analyzed as the STA. We have MMMC, right? Multi-mode, multi-corner. Similarly, we should also analyze CDC with multi-mode, right? And this is how you complete your coverage, right? So if there are clock muxes with multiple clock domain, user needs to choose one mode of analysis, right? But that's one mode of CDC analysis. However, you have to have multiple CDC mode of analysis, and that is the reason this multi-mode CDC methodology helped us a lot. We had parallel 4 mode of analysis, which was, you know, the in the PCI mode, in the SATA mode, the bypass mode, the debug mode. There were multiple modes of analysis which actually helped us a lot in reducing the RDC paths.
Oh, have we lost Rohit? Is anybody else able to hear me?
I hear you, yeah, Carsten, yeah.
We'll give Rohit another minute if he doesn't manage to come. Yeah, could be around about there somewhere.
Okay, so yeah, maybe I think I can start from here. So yeah, I'll take 7 to 8 minutes from here. Okay.
That would be perfect. Has anybody else got some questions getting to here? People followed Rohit's slide so far. Please use the chat if you. I don't currently have anybody answering in the chat.
Okay, so let me just get started, and I'll complete it maybe in 8 minutes. Okay, so uh, this is the last methodology initiative I was talking about, which is power aware CDC verification. So one of the challenge in all the previous projects, right, in the front end CDC sign off, we don't have the UPF instrumented, and that's the reason the power control logic is not connected in the RTL, and that's mainly results in a lot of issues down the chain. So in the absence of UPF, right, since power control logic is not connected, our CDC analysis is not complete. So in order to ensure that even all these low power cells, when it does not bring up any new challenge, right, we need to make sure that UPF, the CDC analysis have to be done with UPF aware, right? And these UPF aware CDC brings new artifacts like power domain are added, the isolation strategies are added, the retention strategies are added, right? Once these strategies are added in place, right, in that case, the new CDC paths get created. For example, if you see the first picture, the power domain to power domain 2, right, there was no synchronizer and there's single path. However, once the CDC the instrumentation happens, the new isolation cell logic gets added, right? Now there is a new CDC path which is from green ISO enable all the way to power domain 2. So this is a new CDC path which was not even visible in the front end RTL. And another challenge is, suppose you already have the last figure, the rightmost, in power domain 1 to power domain 2, there is already a synchronized circuit. So from orange to yellow, there is already a synchronized CDC path, right? But once the mux isolation mux is added, there is a already existing path which was very glitch free. Now there is a isolation cell added. Now because of that, this isolation logic can bring glitches in the design, because this mux can get implemented it and an or kind of logic, right? So we need to ensure that our CDC is actually very much aware of the UPF, and all the low power cells are very much in taken care, and those CDC challenges are addressed with UPF, right? So the second part is the random delay simulation. This is the last initiative I talked about. So basically, the dynamic CDC verification that have to be done using this metastability injection, right? So we call it CDC jitter analysis, and that's basically the random delay simulation happens, and wherein the fault injection which is actually added. But earlier in all the previous way, even if we used to do the random delay simulation, we did not have any debuggability capability, and also there was no coverage, right? I mean, if the violation comes up, it's fine. Otherwise, there's no way to ensure that all your design is actually taken care. So that is the reason this dynamic jitter solution, it generates a better control signal jitter injection model for CDC convergence. And also when we do the random delay simulation, right, we ensure that the synchronizer output, right, I mean, we are actually checking with n plus 3 to n minus 3, right, where n is the destination class. Random delays are actually checked for all the destination combination of the cycles, right? So that is how the solution is actually taken care. Now to conclude and summarize, right, we have seen we have tried to quantify how the coverage has improved from our previous project to the current project. So in the previous project, we used to have the waiver mechanism, but almost only 60% of the waiver were actually translated. However, in the current project, we have ensured that more than 90% of the waivers are actually translated into constraint, and the 10% are only because of the mismatches, IP SoC mismatches issues or the virtual issues. Other than that, everything has been translated into constraints. The second one is, in the previous project, we never had any mechanism to validate. So most of the validation were because of the handwritten assertions which were validated into the simulation environment. Now in the current flow, we have the SVA protocol validation mechanism, wherein we generate we run the CDC functional goal, and we generate the SVA protocol out of it, and those SVAs are binded into the simulation environment to do the validation, right? And third one is the CDC coverage. As I said, right, earlier we only had the single mode of operation CDC analysis. Now we ensured that wherever there was a multiple modes of operations, be it functional, DFD, tab, visa, anything, right? We have ensured that CDC is run for those modes, and it is actually the sign off is done with those modes of operations as well. uh, and the last one is the CDC execution efficiency. When we say execution efficiency, as I discussed, design independent quality check, that was the first one. Earlier we didn't have any mechanism, so until the SoC integration is complete, we can't provide the feedback to IP or subsystem. Another one is the parameter, right? For example, now we have a mechanism to identify which are the critical parameter, which are the don't care parameter. And don't care parameter, we don't need to go and revisit the abstract model or the hierarchical model. In that case, the iteration is shortened much in a much effective manner. Let's talk about the ROIs. For each methodology, I'm talking about the ROI. So for the design independent quality check, we have had at least 3 to 4 weeks of schedule saving, right? So that helps in the TAT. The second one is the waiver mechanism. In that case, once we have all the waiver, it has helped us in the 30% runtime reduction of the CDC analysis. The third one is the CDC validation. Now it has definitely given lot of bugs we have found, because some of the assumptions which were taken for the earlier CDC sign off, those are not holding true, right? And the fourth one is the reset sequences. Now this is about the left shifting. Earlier, based on the RDC violation, RDC data, we used to give the data to the architecture design and they used to validate. So this is like a left shift. Now everything is defined in the master clock spreadsheet and the micro architectural specification document. The fifth one is the multi-mode CDC analysis. We already discussed. It has definitely given the quality better coverage because of the different modes of CDC analysis. The parameters, the handling of parameters also, right? Many time we have to go and request for the IP owners to provide a new collaterals, which is very difficult. So this has given us 3 to 4 weeks of schedule saving. Power over CDC, as I mentioned, that since earlier no way there was no mechanism to enhance it, so now we have a mechanism to validate UPF aware CDC, right? And the last one is the random delay simulation, which also is the quality initiative, right? So yeah, all in all, these are the different kind of initiative we have adopted in order to ensure that our CDC coverage is high, and we also developed a mechanism to quantify those coverage. So that's all from my side. Thank you. Any questions?
Thank you very much, Rohit. Let's see if we've got any questions. Is there anybody on the call who would like to ask a question of Rohit? We have a couple of minutes in hand, which is great. No? In which case, we'll move on to